Hello. I'll give it maybe 1 minute before I get started. I hope everyone's term is going well so far. Hope everyone's year is going okay so far. We'll be talking about today 2 things plus an opportunity for Q&A. So the first thing I'll talk about is the Stats Weekly Application to Games, or SWAG for short. A few years ago, my class made up that acronym for me. So that'll be the first thing. And for today, we're going to talk about Texas Hold'em, which is a game that I am terrible at, but there's some interesting probabilities involved. Then we're going to talk about machine learning. So I have a machine learning idea of the week. The acronym Stats Weekly Application to Games. So it's SWAG. I guess Friday we get our swag. And then machine learning idea of the week is MLIW, which is a not very interesting acronym. So if anyone can suggest a better acronym for my machine learning idea of the week, I would appreciate it. And then when I've done that, we have time for Q&A. So if anyone has any questions about anything in the course so far, or we'll focus on course-related questions first, but if you also have other sort of extension questions, we can talk about that as well. So it's 2:02, so let's get going. So again, thanks everyone for joining. I will be recording this and posting it on Learn, probably editing out the first little bit, but I'll be posting these videos and the text here, the PDF that I'm looking at. I'll put that on Learn as well, so you can check that out. So if you don't know how Texas Hold'em poker works, this is how it works. Every player gets 2 cards face down from a standard deck, which is 52 cards. There's 4 suits, and then there's 13 different ranks within each suit. And then 5 cards are dealt face up, and those cards are shared between all the players. And then those cards don't come down all at once. They come down first. 3 is the flop, the 4th is the turn, and the 5th is the river. And after each of those, there's a round of betting, and then you're trying to basically create the best poker hand they can from all 7 cards, your 2 personal cards and the 5 shared cards. So I'm, as I mentioned, terrible at this game, and the reason I'm so terrible is that A, I have no poker face, but B, I always go after straights. Straight is 5 cards in a row in terms of their rank, whether or not they're in the same suit. So it could be like 3, 4, 5, 6, 7 of any suits, that would be a straight. Or 10, Jack, Queen, King, Ace of any suits, that would be a really, really good straight. So imagine that we're playing this game and I have a 7 and a 9. Oops, I'm going to try and get myself a little pen here so I can mark this up. I have a 7 and a 9. And the flop comes down 6, 10, ace. And that looks really good because I have a 6, a 7, a 9, and a 10. And if I got an 8, I would have a straight. And I am so excited about straights. They look so cool. This kind of thing is called an inside straight draw because we need an 8 to complete that straight. So I want to know, what is the probability that I get this? Whether I get it on the very next card on the turn, or on the river if it doesn't come on the turn, or anywhere within the next 2 cards. One thing that is important to think about, though, is does it matter how many people are playing this game? You would think that it probably would matter, but actually the cool thing is that it doesn't. Basically, any card that I can't see is equally likely to be any of the cards that I can't see. So it actually doesn't matter how many other people are playing, or whether we've played a few rounds before, or whether cards have been burned or put face down by the dealer. Any card that I can't see is equally likely to be the next card that comes up. Now, of course, if I was really good at reading people and I had a sense of, what people might have had in their hands, or if someone had put their hand face up when they folded, then I would take that information into account. But unless I can see the card, it's every card that I can't see is equally likely to be the next card out of the deck. So take a second, think about that, convince yourself of that. So what we want to do then is think about using just classical probability here. What's the probability of getting an 8 on the turn? Well, there are 47 cards that I can't see. Right? There's 5 face up that I can see. There's 2 in my hand that I can see, and the deck is 52 cards. So if I take 52 minus the 7 I can see, I can only see 3, right? I know how math works. There's only 3 down on the table so far, the 6, the 10, and the ace. So there's 3 down, 2 in my hand, 5 total that I can see, and thus the other 47 cards that I can't see, each of those is equally likely to be the next one out of the deck. And 4 of those are 8s. So the probability that I get an 8 on the very next card, by the classical definition, is just 4 over 47. If someone has an 8 in their hand, that doesn't matter. Like if I don't know they have an 8, then I can't use that information. So it's just straight up 4 over 47, which is only about 8.5%, so not particularly likely. Let's say we don't get an 8 on the turn. What's the probability of getting an 8 on the river, given that it didn't happen on the turn? Well, now at this point, there's 46 cards left in the deck, because whatever came on the turn I can see now, and there's still 4 8s left in terms of the cards that I can't see, so we have just 4 over 46, which is 8.7%. What about just, in general, the probability that I complete my inside straight, the probability of getting an 8 anywhere in the next 2 cards? Unfortunately, we cannot just add up these two probabilities. We can't just take 8.5 and 8.7 and add them up. And why not? Rhetorical question, because I know you can't respond quickly enough, but think about to yourself, why can't we just add those things up? The reason is that will double count the cases where there's an 8 on the turn and the river. So it would overestimate the probability if we just added up those two. So there's a few different ways we could actually calculate it. Here's one way. We could basically just use the addition rule and the multiplication rule and sort of look at this in terms of 3 cases. So there's 3 here, mutually exclusive or disjoint or distinct cases. We could either have an 8 on the turn and not on the river. We could have not an 8 on the turn and an 8 on the river, or we could have an 8 on both. And for each of those, we look at those probabilities. So 4 8s out of the 47, and then 43 non-8s out of the 46 next cards. Same thing here, and then same thing here. 4 and 3, because once we get 1 8, then there's only 3 8s left in the deck, and then there. So each of those is using the multiplication rule, because we need an 8 on the turn and a not 8 on the river. And in probability and means you multiply. Now we have those 3 cases, and they're mutually exclusive. And so we're going to add those up, because we want one or the other of those 3 cases. And so we just add those up, because by the addition rule, or in probability means adding. So if we add up those 3 cases, we get a big old 16.5-ish%. So not very likely, about 1 in 6 chance of completing your inside straight draw, which is not very good, which is why I am so bad at poker, because I always chase after these. So don't play poker with me. Or, I mean, you probably want to play poker with me, but I'm not going to let you, because I'll just lose all my money. All right, cool. So that's an inside straight draw. There's other types of straight draws as well. So I just want to fairly quickly talk about this other case here, a couple other cases. So we could have something like, if I had 7-9 at the beginning, and the flop was, say, 6-8 king, then I have 6-7-8-9 in a row. So a 5 or a 10 would give me a straight. And this is called an open-ended straight draw rather than an inside straight draw, because either end would give me that straight. And so we can do basically the same type of calculation here. The probability of getting a 5 or a 10 on the very next card. Now there's 8 5s or 10s in the deck, so the probability is about 17%. Similarly, we can split it up into 3 cases and calculate overall that the probability is about 31.5%. So closer to 1/3. Not quite twice as likely, but almost twice as likely as an inside straight draw. And then finally, this is an even, I guess, less likely case to complete. What if you need 2 extra cards to make your straight? So you have 7 and 9. The flop is 2-5 king. So you would need both a 6 and an 8 to complete the straight. So that's super, super unlikely that you would get both a 6 and an 8. And if you want to calculate that probability, there's only 2 possibilities. Either we get a 6 first and then an 8, or an 8 first and then a 6. There's no other ways. And so the probability of that is fairly low. Overall, only about 1.5%. So that's just some info about poker in general. There's lots of really great probabilities in terms of calculating probabilities of different poker hands. I'll see if I can find, at one point I found a really nice rundown of all of those calculations. And all of these calculations just use the techniques that we've used in Chapter 3 in probability. So you can look at the probability of getting, a straight flush or a full house or various other types of poker hands. Alrighty, any other questions? Oh, application of probability to Go Fish. Love it. Minesweeper, Go Fish. Okay, I will write those down. Great. Okay, so then the next thing I want to do is just a quick glance. Among Us, yeah, definitely. I'm sure there's lots of probability involved in Among Us. There's a lot of social gaming too, which is harder to model with probability. So then I'm going to go as well and check out my machine learning idea of the week. And this is fairly short, just to give you a brief idea in terms of some of the common machine learning problems that machine learning can help with. Each week I'll have, again, a little bit more, and this is going to be very, very high level. I'm not going to get into the technical details. Oh, rock, paper, scissors. Love it. Good one. Theoretically, it would be random, but it's not, because people use information about each other's previous plays to decide what to play next in rock, paper, scissors. Love it. Great. Chance of being imposter. Chance of being sus. Yep. I get it. Okay, so machine learning ideas. What I want to talk about today, again, is just some typical problems, and this is like a really broad classification of types of problems. So the first type of problem that machine learning can be useful for is classification. And that's just, again, a broad category of problems which are basically determining what type an object is based on its characteristics. So the sort of the outcome that you get is a category for something. So whether that's could be determining whether a piece of email that comes into an inbox is spam or legitimate. It could be determining based on some data from a tumor whether the tumor is cancerous or benign. It could be any kind of just like diagnosis of any kind, so any disease at all. So the key with classification is that it's categorizing the object into one of two or more types, and based on the characteristics that it has. So that's one sort of type of machine learning algorithm. Another type is regression or function estimation. And so this is kind of similar. We're taking various characteristics of the object, but then rather than assigning it to a category, we're assigning a number to it, a value. So the difference between classification and regression or function estimation is actually kind of like the difference between discrete and continuous sample spaces, if you want to think about it that way. So the regression or function estimation, we're basically taking everything we know about this object and then trying to estimate a value for it. What value should we assign to it? A great example would be the price of a house. So like you can take, the number of bedrooms and like where it is and like how, I don't know, like the size of the lot or the square footage of the house or how many bathrooms or whatever, bedrooms, whatever. And then use that to predict what the price should be. And of course, there's other intangible things, so there's going to be some randomness around that, but that might be an example. Another thing would be like recovery time, so estimating how long it might take someone to recover from cancer based on the severity of their symptoms and their genetic history and when the cancer was discovered and blah, blah, blah. So that kind of thing. Or even just in sort of like an actuarial context, estimating future lifetimes of people. So lots of different ways you could do that, function estimation or regression. And then another type of problem to solve would be something like clustering. So in that case, you're not trying to assign objects to a category, and you're not trying to assign a value to each object. You're just trying to group objects together based on similar characteristics. So this is really common in things like looking at customer experience, what people have bought together and how they spend their money. And that could be obviously used for marketing, because if there's certain customers that have similar characteristics, they tend to always buy, this thing as soon as it comes out. They're sort of alpha consumers that generally like buy things very quickly. Then you might market to that group differently than you might market to another group. It could be in sort of a finance context, the way people spend money or the way they use their financial transactions. Another great thing is news stories. So a news aggregator might take stories that are similar and group them together. And it's not like a person is standing there looking at each story and saying, okay, this goes under this goes under this. They're looking at words in the stories. The algorithm is looking at words in the stories and then grouping them together based on these characteristics. So lots of different ways that you could use clustering to do that. If you created a machine learning problem to classify objects into a countably infinite sample space, would it function like a regression estimation? That is an excellent question. And yes, at that point, it would be more like a regression rather than a categorization or a classification problem. Yeah, classification, you can have many different categories, but as soon as you get to like countably infinite, then I think that it might be better to do it with a function estimation. So that's a good point there, that when I said it's kind of like the distinction between discrete and continuous, I lied a little bit because it's not quite the same thing. Thank you for mentioning that. We have to solve these problems. No, you don't. Oh my gosh, no. This is just to give you an idea of how machine learning can be used. And probability, like what we learn in this course, is the basis for a lot of machine learning algorithms. So no, I promise you won't have to solve these kinds of problems yourselves. Though you can take courses if you're interested. There's plenty of courses in UW's programs that do talk about these problems. All right. I think that's all I wanted to say about this. Yeah, so I think I will just open a blank page here or something, or just scroll down. There we go, blank page. So I'm open now to questions either about machine learning or about the swag that I just talked about or about anything in the course at all. Oh, can you train a machine learning program to train machine learning programs? Oh my goodness. I believe yes. And I, for one, welcome our new robot overlords. But yeah, I think yes. I don't know a lot about that, but that's a really, really cool suggestion. And if you know of a good article you've seen anywhere, feel free to post on Piazza or something. Maybe I'll start a tag on Piazza for swag and machine learning idea of the week, just in case there's other resources that I want to share or that you find out. What is the probability they wipe us out in the next 50 years? That is an excellent question. And you know, what type of probability would I be using if I gave an answer to that question? That would be subjective probability, because I have no idea. I'm gonna put on my optimistic face and say low. Yeah, subjective, absolutely. Oh, Pavel Shu, no, that's a flagrant violation of the assumptions of the classical definition of probability. Boo! I mean, I think you did that on purpose. But yeah, classical probability only works if all your outcomes are equally likely. Then you could say 50-50. Because if not, I could say, yeah, I knew you knew. If not, my favorite example is, okay, I'm going to buy a lottery ticket. Either I win or I don't win. So I have a 50% chance of winning the lottery. Why wouldn't I play the lottery? It doesn't work that way. So yeah, we need equal probability for the classical definition. Yeah, very subjective. Okay, so are there any questions about the course material so far? So in the first 3 chapters, basically, we've looked at definitions of probability. We've looked at a little bit of theory in terms of sample spaces, events, and various ways of counting numbers of events. So I see a few questions came in at once, and I will try and go through them in order. Keep them coming, though. I'll try and get to everything. Oh, nice. There are machine learning algorithms called generative adversarial network. Fabulous. So definitely I will look into that, because that sounds neat, which is basically, yeah, it's going to be an algorithm that generates more algorithms. Very cool. By relative frequency, I've been alive for every second of my life, and so do have a near 100% of chance of being alive at any point in time. That's a great question as well. Remember, with the relative frequency definition, it's required that the experiment or whatever you're doing is repeated under the same conditions an infinite number of times. And unfortunately, your body is not in the same condition it is 19 years ago or however long. I know mine certainly isn't. So yeah, that's a cool idea. And actually there is a model for future lifetimes, which we'll talk about when we get to chapter 8, I think, which is called the exponential distribution. And that's a distribution that basically says, no matter how long you've already been waiting, the future waiting time is unchanged. So that's obviously a not very useful model to use for human lifetimes, because that would be saying that the probability that a 101-year-old lives to see 102 is the same as the probability that a 21-year-old lives to see 22. So that's obviously not applicable to human lifetimes, but it's sometimes used in the short term, or maybe for the reliability of certain mechanical or electrical components. Is it possible for you to go over when to use n to k factors, n factorial, and n to the k? Absolutely. That is a great question, and I will do that. So I'm going to just write down here. Can I... give me this. Green pen. Why not? Okay, so basically what I want to start with is backing up just a tiny little bit. Whenever you're looking at a problem, like a chapter 3 type problem, where you're counting a number of things, you want to ask yourself 2 questions. First of all, can we get the same object twice? So sorry, my writing is a bit messy here. Can we get the same object twice? If the answer is yes, then we know that we're sampling with replacement. So if it's yes, then that is sampling with replacement. And then we know we're going to use n to the k, because every time we select an object, we still have n choices. So we're not losing any, we're not wasting things out or like using things up. So we're going to use n to the power of k if we're sampling with replacement. And then if the answer is no, then we move on to question 2, because that's also important. So question 2, if the answer is no, so we cannot get the same object twice, then we ask, does the order of selection matter? So is it the same thing if we get object 1 and then object 2, or object 2 and then object 1? Is that the same thing? So an example of where it would be the same thing, where the order would not matter, would be like drawing a hand of cards. Because if we're drawing a hand of cards, we can hold the cards and then we can just order them in whatever order we like. But if we're creating a password or something where we're not allowed to repeat digits for some reason, then the order of selection does matter. Or like assembling the Enigma machine. There's a great example in the end of chapter problems that I wrote, where it's talking about the order of the disks in the Enigma machine. It's going to be different whether we select 5, 1, and 3, or 3, 1, and 5, or 1, 5, and 3, etc. So we want to think about, does the order in which we select those objects matter or not? And if it does, then we have a permutation. And that means we're going to use n to k factors. So that's the way we say that, is n to k factors, to differentiate it from n to the k. And remember, that's just, n times n minus 1 times n minus 2, etc., down to n minus k plus 1. So there's k terms in that product, and each one of them is one less than the one before. Whereas n choose k is n times n times n times n times n, etc. So if the order matters and we're selecting without replacement, then we use n to k factors. And if it's a no, if the order does not matter, then it's a combination. And that's when we would use n choose k, which is just n to k factors divided by k factorial. Or equivalently, n factorial over k factorial, n minus k factorial. Oops, sorry for squeezing off the end there. So does that help the person who asked that question? All right. Hopefully, yes. If you have a follow-up, please feel free to post. Can you give an example of uncountable infinity? Oh, great. Thanks. Glad that helped. Yes. Okay. Uncountable infinity is something that cannot be put into a one-to-one correspondence with the integers. So countable infinity is, I hate the word countable. It should be called listable. That's a much better word for it. I'm going to campaign, because countable sounds like you would get to stop. You might not stop counting, but you could list them. You could put them into an order, and I could ask, okay, where is this particular item? And you could tell me where it would be in the list. So a countable set is one where you could find any item. You could tell me where it would be in the list. That's what countable means. So it can be infinite. There can be infinitely many of them, but they have to be able to be put into some list that we know where every item is. Might be a long way from now, but we have to be able to find it. Uncountable means we can't possibly do that. Any list we create, there's going to be some items that we say, where is it? And we say, oh crap, we forgot it. It's not in the list. Let's add it. Okay, well, where's this? Oh crap, we forgot that too. So that's, I see someone just said Aleph 0. That's exactly right. So Aleph naught, or Aleph 0, is the cardinality, the size of any countably infinite set. And Aleph 1 is the cardinality, or the size of any uncountably infinite set. So an example of an uncountably infinite set would be the set of real numbers. So any real number. Oh, a question, just when does n factorial come in? N factorial is just n to n factors. So that would be here. So if we're taking all of the objects and putting them into order, that's n factorial. Yes, oh thanks, huge nerd. I get it, huge nerd, good one. That's right. Okay, sorry, so back to infinite sets. The real numbers are uncountably infinite because anytime if you try to create a list of real numbers, I could create a real number and say, where is it? And you would not be able to tell me. If you want to look at the proof of this, you could look up Cantor's diagonalization argument. I think I posted a link to it on Piazza, but maybe I'll repost it somewhere. But that's basically how you can create a contradiction to the real numbers being countable. So the real numbers are uncountable, and so are the complex numbers, and other things like that. But the rational numbers are actually countable, which seems kind of weird because you can be like, how can you put the rational numbers into an order? There's a cool way of doing that as well. So I suggest checking out just Google proof that rationals are countable. There's some really, really great videos explaining it. But hopefully that helps. So uncountable would be something like the real numbers, where it can take any real value, whereas anything that you could list in some kind of order is countable, even if it's infinite. Okay, great. Pearl Kang asks, will the quiz questions be similar to the questions from lessons or textbook? I would say, yeah, they're pretty similar. I wrote a bunch of them. A bunch of them were taken from old tests that I wrote as well. But there's also a bunch, I think there's over 1,000 questions in the question bank. Not that you have 1,000 questions to do, you only have 10 questions on quiz 1. But when I look at them, they look like similar difficulty to me. And they would be sort of maybe even a little bit easier because they're one-part questions. It's not like a question 1, A, B, C, D, blah, blah, blah. It's just sort of like one answer that you have to give. Some of them are multiple choice, and some of them are like you have to fill in a numerical answer. Pijun asks, are there more places to find practice problems outside of the course notes? There's a lot of great ones in the course notes. So if you've done all of the questions in the course notes at the end of section problems and the end of chapter problems, and you're comfortable with all of that, I think you're well on your way. I could recommend the MathSoc exam bank if you're in math. I think even if you're not in math, you can access that. So you can see past tests, although the difficulty might be a little bit different just because it was a different term. So that might be a place that you can look. We don't have a recommended textbook, like the course notes is our textbook, but you could probably Google practice problems probability and find something. Or honestly, I promise I'm not just trying to get you to do my job for me, make up problems and then trade with a friend. Or if you don't have any friends, make a friend. So like outside of the collaborative assignment, which is where you're going to have to make up a problem like for marks, but it's actually not too hard to make up problems. And if you make up a problem and then solve it yourself, it's not quite as interesting. So if you make up a problem and your friend makes up a problem and you swap, you might be able to find some interesting applications that way. So I kind of, just the way I live my life, whenever I'm like in the world, I think, oh, what would be the probability of that? It just happens all the time. That's just how my brain works. I'm like playing a game with my kids or putting something together, like building some Lego. I'm like, I wonder how many ways there are to attach 2 pieces of Lego. So just thinking about how probability can be applied to lots of different situations. And hopefully that gives you a couple of ideas. So MathSoc exam bank, Google practice problems, Khan Academy probably has some good stuff. Everything in the course notes first, start with that stuff. And then also try and make up some problems and switch with a friend. Okay, questions. Can we think about having n possible choices as a tree? Yeah, I guess. Yeah, you could think about it that way. Yeah, kind of like, so if there's n choices, then yeah, if that helps you visualize, absolutely, that's great. I always draw out, like when I'm thinking of like how to, build a password with all even digits or like the first digit bigger than the second digit or something like that. I always draw it out because I find it so much easier to visualize probability. But everyone's brain works differently, so do what works for you. So n to k factors is equivalent to npk. Yes, those are the same thing. So let me add that here. N to k factors is also known as, I'm going to change the color of this pen here, so purple, why not? It's also known as npk, and n choose k is also known as nck. So you absolutely, if you're more familiar with those terms, that's the equivalence. Yeah. Okay, blah, 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 blah. Good questions. Okay, for countable / listable integers, what if we choose both the negative and positive? Ooh, okay, I love that question. So yes, all the integers, including the negative and positive, is still listable. And I'm gonna prove it because that sounds like so much fun. Okay, I'm gonna erase all this. So imagine we've got the integers, all the integers, and we wanna put them into an order. So I'm going to start with 0, because why not? And I can't just go up, and then when I get to the end, go negative, because there is no end. So what I can do is alternate. So I could go 1, -1, 2, -2, 3, spoiler alert, -3, etc. Oh, my face is covering up the 3, sorry, 3, -3, etc. So this set is not in order of biggest to smallest or anything like that, but you could tell me where any integer is. If you asked where is -4,362, I could tell you where it is. I'm not going to do the math in my head, but I could tell you. I know where it would appear. So that's how we can get the integers, all integers positive and negative, in an order in terms of a map to like listing them in a particular order. So that's pretty cool. Hopefully that helps. And for the rational numbers, just in case anyone wants to see, Q is rational numbers, right? It's been so long. There's a really cool way to write the rational numbers as a countable set. And I just want to give you a hint because it's just so cool. So imagine you start off with your rational numbers like this. We've got 0, and then we got, let's just do positive rational numbers for now. 1, 2, 3, 4, whatever. Do. And then we'll have like 0 over 2, 1 over 2, 2 over 2, 3 over 2, 4 over 2, etc. And then we'll have 0 over 3, 1 over 3, 2 over 3, 3 over 3, 4 over 3, etc. You get the idea. 4 over 4, blah, blah, blah. So we keep going in both directions. Again, I'm just going to do the positive rational numbers for now, or non-negative rational numbers. I want to create a list of these numbers that's going to catch every single one. So what I'm going to do is do this. I'm going to start here at 0. If I ever get to a number that I've already done, I'm going to just skip it. And then I'm going to go through the numbers like this. I'm going to go here, and then I'm going to go here, and then I'm going to go here, and then here, and then here. Wah, wah, wah. You get the idea. So you can snake your way through this infinite matrix, basically, of rational numbers. And that gives you an ordering that will hit every single rational number that's positive here eventually. So that's how you can make the rational numbers be countable as well. I know you didn't ask that, but I wanted to address that because it's just pretty cool. Alrighty, I'm sorry, I'm sort of confused about what you mean if we can get the same object twice. Like throwing a die multiple times would give us same objects, but rearranging letters in a 4-letter word would not. What if I just decide to rearrange the 4-letter word as something I arranged it as before? Okay, I think I see what your question is. So when I talked about can you get the same object twice, I guess what I mean is if you're sort of filling in spaces, either in series of dice rolls or digits in a password or cards in a sequence or whatever, could you have the same number fill each square? So if you're rolling a die and you roll a 1 on the first one, you could absolutely roll another 1. So you could roll a 1 and then maybe you roll a 6 and then you could roll a 1 again. So you can roll a 1 a second time. But if instead you had, say, a deck of cards with the numbers 1 through 6 on it, and you were drawing the card and recording the number and then putting the card aside, so not putting it back into the deck, then you wouldn't be able to get the same object a second time. So the object isn't the entire arrangement. The object is each individual element that's going into those spaces. So could we get a second 1? Sure we could if we're rolling a die. If we're drawing cards without putting them back in the deck, could we get the same exact card again? No, because we're not putting it back in. If it's talking about rearranging letters in a word and the word has the word is word, there we go, word is a 4-letter word with 4 different letters. If we're rearranging those letters, we're not allowed to pick the same letter twice. So we can get like rod or like rod or like various other things, but we have to use each of the letters exactly once if we're talking about sort of rearranging the letters. So that would be a case where we're not allowed to yet use the same object twice. If we somehow wanted to if we started with like an alphabet, like A, B, C, D, E, whatever, and we wanted to just create a string from it where we were allowed to choose the same letter twice, then that would be fine. So in general, like if you're writing a password, you're absolutely allowed to use the same letter or number more than once. So sometimes if it's ever not clear, we'll probably tell you, but something like you're writing a password or creating a PIN, like a personal identification number, we don't have to tell you that you're allowed to use the same object twice. Of course you are. And the example, there was an example of like, in the course notes, I can't remember which one it was. There's different cars that have faulty engines and an inspector is checking 8 of them. We don't need to tell you that obviously the inspector is not going to check the same car twice. They're going to be checking 8 different cars. So that would be a case where by the nature of the problem, you can tell that we're not going to get the same object twice. So hopefully that makes some amount of sense. Let me know if that doesn't. Okay, some great answers to the integers question. Is generating function part of this course? We will, at the very end, talk about moment generating functions, which is one type of generating function, fairly briefly. But if you want more info about generating functions, Stat 330 is a great course for that. Yeah, I think section 4.6 is pretty neat. It's some cool summation results. We're not going to get you to just like memorize all of those results. Like they're useful to know, but what they're most useful for is proving that various distributions are valid and add up to 1, and also to find like the mean or variance of those distributions. So we'll use 4.6 to help us out in chapter 5 and chapter 7. Great job. A nice response to the rational number question. What is the probability that given 2 bingo tickets, at least one number will collide? Okay, that's a great question. I am going to answer it. Okay, so great question. Bingo cards. Someone might have to remind me what bingo cards look like. So there's 5 numbers in each column. Oh no, there's 5 numbers in the first, second, fourth, and fifth, and there's only 4 numbers in the middle column because there's a free space. So it's like doot, 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 and this space is a free space. And then the B has to be between 1 and 15, is that right? Yeah, so under the B column, we're going to choose 5 numbers without replacement, because the bingo card can't have 2 of the same number on it, from 15 possible numbers. When you say collision, do you mean like exactly the same number in exactly the same spot? Or do you mean just having the same number? Because that's an important distinction, because if it's 1, then it's going to be where we care about the order, and if it's the other, then it's going to be that we don't care about the order. So I'll give you a second to maybe think about same spot. Okay, so in that case, we do care about the order. So the number of ways to fill in the column of B's, we've got selecting without replacement, order does matter, and we're selecting 5 objects from 15. So that's going to be, think about it before I say it, 15 to 5 factors, ways to do that, right? N to k factors. Same for I, 15 to 5 factors. N is going to be 15 to 4 factors. That's a 4 there, sorry. G will be 15 to 5 factors, and O will be 15 to 5 factors. So that's how many possible bingo cards there are. Holy moly, that's a lot of bingo cards. So the question is, what is the probability of 2 bingo cards having at least 1 collision? And I think the best way to calculate that would be to use the complement. So a really good trick sometimes is, instead of trying to calculate the probability directly of the event that we're giving you, think about the opposite of that event. It's often easier, especially if the words "at least" appear in the question. So the opposite event of that, 2 bingo tickets, at least one number colliding, the opposite of that is no numbers colliding. So none in the exact same spot. So I think that's how I would want to calculate that. I would want to calculate the probability of having, given one card, having another card that has none in the exact same spot, and then take 1 minus that. So I think that's actually harder than I originally thought when I started just solving this problem. So maybe I will let you think about that, use that strategy. Maybe I'll make it one of the thought questions, and then tell you the answer later. So copy that question. You can give this is the total number of bingo cards, which is a lot, actually. It's going to be a huge number of cards, and then see where people get with that. But thank you for the question. Great one. Don't forget that if you haven't yet, make sure you do Mobius Quiz 1 by next Wednesday night. You do have 3 attempts, so I strongly encourage you to do 1 attempt at least this week, for several reasons. 1, to test that your computer works and everything works out, because if you run into technical difficulties and you need help from emailing learnhelp@uwaterloo.ca, you don't want that to be happening when you're under extreme time pressure. So definitely give it a try. And also, it can be a really good diagnostic, right? If you've watched the lecture videos and you've tried some of the practice problems and you think, yeah, okay, I think I have a pretty good handle on this, and then you try the quiz. If you do great on it, then awesome, you were right, you did know that stuff. If you do not so great, or you're not happy with your mark, then you can spend a little bit more time maybe reading the course notes in more detail, trying a few more practice problems, bouncing ideas off each other on Piazza, etc., until you feel comfortable with the material, and then you can try your second attempt, and then your third if it's you're not happy with it. So again, I do strongly encourage you to use at least your first attempt this week, if you're not already completely done. And then next week, you can start on the week 2 material, which is covering the rest of chapter 3 and most of chapter 4, I think about half of it. And then there'll be another Mobius quiz that opens on Wednesday and closes the following Wednesday as well. It's Mobius for the first 2 weeks, and then there's more breaks between the rest of the Mobius quizzes. All right. Oh, can we use Piazza for those example thought questions that we made up? Yes, absolutely. Like, if you have a question that you've made up and you think is cool, go post it on Piazza. Yeah, that's great. I was imagining that I would use the thought questions tag just for like the thought questions and the polls that I ask. But if you have a question that's just kind of cool and you want people to think about it, then you can tag it with thought question. And if I think it's not appropriate, then I'll just untag it as that and tag it as the appropriate chapter. But yeah, if you think of a question on chapter 3 material, you can tag it as chapter 3. You might want to save it though for your collaborative assignment. So if you have a really good one, you might want to hang on to it, because your collaborative assignment is going to be that same idea, that you create a question, maybe like a multiple part question, and then some of your teammates are going to solve it. So if you have one that's super cool, then maybe hang on to it. But if you're just really excited about getting people's thoughts about something, or you're not sure how to do it, but you think it must be possible, then absolutely you can post on Piazza. I did put, just in case you didn't see, some guidelines for titles of posts on Piazza, just to try and keep things a little bit organized, that it would be great if people could follow, but just using the tags is a really good way to keep Piazza organized. Oh, another question. If you flip a coin 3 times and roll a dice twice, heads equals 1, tails equals 2, sum everything together, and if it's even, do nothing. If it's odd, I should have read the whole question first. If it's odd, pull the handle and change the tracks. What are the odds that in the trolley problem you'll make the morally correct choice? I love that. So yes, if you're not familiar with the trolley problem, there's a trolley going down a track that's about to kill 5 people. And you can flip a switch, and then the train will change tracks and then kill only 1 person. So it's sort of an ethics thought experiment of like, would you pull the switch? It's like, obviously in the abstract, it's better for 5 people to survive and 1 not to than the other way around. But it feels weird because if you do nothing, then you're not responsible. But if you actually pull the switch, then you're responsible for the death of that one person. So yes, definitely way beyond the scope of this course. We're not going to talk about philosophical ethics, although if that sounds interesting, I highly recommend the show The Good Place. It's just absolutely fabulous. Good Place, great show. Teaches you lots about ethics. Okay, so do you actually want me to calculate that, or was that just a long roundabout way to make a yeah, hold on. If you flip a coin 3 times and roll a die twice, sum everything together, and if it's even, do nothing. Yeah, I think it's still 50-50. Yeah, it's going to be 50-50. Because the sum on, if you think about rolling a dice twice, it's the 36 possibilities that you get, exactly half of them are even. And if you flip a coin 3 times, then half the time the sum is going to be even, half the time the sum is going to be odd, so it'll be 50-50. But yeah, it's a still cool question. I like it. You really had me going there until I got to the end. How do you assign groups for collaborative assignments? Great question. So if you know who you want to work with, if you know with whom you want to work, I guess to be fancy about it, then you can select your groups together. There's instructions given on Piazza. If not, if you haven't selected a group by January 22nd, which I believe is the deadline to do that, then we will randomly assign groups. So the collaborative assignment is designed so that you can do it asynchronously. So you don't have to be in the same time zone or anything as the members of your group. It might be a little bit easier if you are in the same time zone as the people in your group, but it will work just fine. We've designed it so that it works okay as an asynchronous activity, because you'll be sort of giving your questions to each other, solving each other's questions, sending them the solutions, and then sending them the critique. So it will be random and amongst the people who have not chosen a group already. So does that make sense? Pick your group yourself if you want to, and if not, you'll be randomly assigned to a group. And then for the second collaborative assignment, the groups will stay the same unless people have dropped the course. So occasionally, of course, for many perfectly legitimate reasons, then people might drop the course. And so we may have to rejig a small number of groups to make sure that there's enough people in each group. And we do want groups of 4 ideally. There might end up being some groups of 3 just because I don't know if the total number of students in the class is congruent to 0 mod 4. It might be. It has a 0.25 probability if we're assuming that number of students is relatively random, although it's probably not. I wonder. Anyway, now I want to know, if I look at all of the class sizes of all classes at Waterloo, how many of them are congruent to 0 mod 4? Not 8.25, 0.25. Okay, well, I'm going to sign off then. Have a great day, folks. Have a great weekend. And stay healthy, stay safe. Bye.